Okay, I don't need to project immediately, but later on I can project. Okay, so I hope you can all see this loud and clear. Yeah. So yeah, this is who the names basically indicate you have got it correctly or mostly correctly. Okay, so I wanted to acknowledge that. Okay, for one, I think you pretty much got. Yeah, so we'll discuss the all three of them one by one. Okay, now. Okay, so one key assumption that most of you had was that it's a rotational symmetry of order 2, or that you are rotating. Okay, which is fine. The question is, why do you rotate by 180 degrees? How can you make it more rigorous? Anybody? Once you get to 180 degrees, the rest is a piece of cake, and which you have got. But why is it a rotation by 180 degrees? Let me break this down. Okay. Okay, I can't see anybody unmuting or writing anything in the chat. So let me break this down a bit. Consider a triangle with rotational symmetry. Okay. Then will it be 180 degree?
No.
Okay. How many degrees? If you have a triangle with rotational symmetry, which triangle is that? And yeah, 60 degree. And what kind of triangle is that?
Equilateral.
Equilateral. Okay. Now, okay. What about a pentagon? Imagine.
$72 maybe.
Okay, 72 degrees. So not 180 degree, right? And this, now here's the thing. For triangle, is it 60 degrees? Are you sure? I'm just going to draw some triangles, etc.
90 degree?
No, just don't. Okay, so this is roughly an equilateral triangle, right? Now, if I rotate it by 60 degree, I'll just take another copy, change color and rotate. Yeah. Okay, now let's rotate.
120 degree.
Okay. Now, how to see that? See, if you rotate it by 60 degree, by the power of technology, you can see what happens, right? I've actually instead by 120 degree, yeah, then it's kind of the same thing, you know, it overlaps, right? So what's going on? One way to think about this is, let me make it a lighter color so that things are easier to see inside. Okay. The center of rotation will be some point here. So let's just draw some lines. Because this will come as an intersection, point of intersection. Okay, so you see where they have all intersected, that is basically that's basically the center of rotation. Now let us now consider these things. Okay, this is an easier way to put it. Okay, how? Okay, okay, no problem. So I can still draw the arcs to show the angle. Now, if you consider this angle, okay, see that is how much right? And let's call the center to be O. Okay. Now you can see if you rotate it by 120 degree, then A will go to B. Okay. Let me change the color so that it becomes very clear what we are talking about. So this is going to be, you know, become, and let's also call this A dash, right? This is where A will be, and this is where B is going to come, and you can understand where C is going to be. So if you look at that, now see the angle by which A has rotated, and that's 120 degree. Okay. Okay. So similarly, now in light of this, can you tell what it is going to be for a pentagon? Is it going to be 72 degrees or something else? Also, I want you to consider a few more. Same question for hexagon, octagon, okay. Let me just reduce it. Let's say a nonagon, which is 9-sided. What will happen for a pentagon? Okay, here's a pentagon to help you think. So in this case, we get 120 degrees. What will we get for hexagon?
60.
Okay. Anything else? Any other possibility other than 60? What about octagon?
45.
Okay. What about nonagon?
40.
Now, what is the basis of this?
So for one complete rotation, I have taken 360 degrees. So I have divided with the side they have.
Okay,
So
now
next time they will map with the
got it. Noted. Now, let me draw a hexagon. Okay. This is a hexagon. Does it have rotational symmetry?
regular hexagon.
It has or no?
It has at the 180.
Okay. And it does it, I mean, will it, if you rotate it by 60 degree, will that work?
For regular hexagon, it will work.
We are not asking about regular. Hello. See, the original question is a quadrilateral with rotational symmetry. Regular though makes life very, very easy, right? So when we are talking about a pentagon or a hexagon, we are not talking regular. It can be regular. In case of a triangle, it becomes regular. True. But there is something more going on. See, for a pentagon also, you can kind of argue out that it may become a regular one. Okay. I'm guessing it is going to be a regular one. And that is something you can try to figure. But for a hexagon, right? For example, in this case, angle of rotation. Sorry, I got disconnected. Resharing. So for this one, what is the angle of rotation? Yeah, my net doesn't seem to be working great today. So I have not, even if you have said, I have not heard. So for this hexagon, and let me remove the pentagon for now. For this hexagon, what is the angle of rotation?
180.
Would somebody please type it in chat? Yes, okay. Now, if I draw a different hexagon, and let me try to draw it. I'm going to annotate here. Okay. So for this hexagon, what would be the angle of rotation? Does it have rotational symmetry? I mean, obviously it is a bit imperfect, but you get the picture. All angles are 120 degree, alternate sides are equal, 3 sides are longer than 3 other sides. This one doesn't have rotational symmetry, okay? Anybody else thinks otherwise?
That's rotational symmetry. 120.
Yeah, feel free to annotate.
When this move was this.
The smaller cannot move to the larger side. They're alternating. but
This side.
this one can, okay, hang on. Yeah, that can move, yes. So this one can move to this one. This one can move to this one. And this one can move to this one. Okay. So in other words,
Three rotation.
imagine it to be a, if you think of it like a triangle like this, and you rotate it, then that is possible, right? Can you see that?
Yes.
Okay, so in now that you see it, what is the angle of rotation?
120.
Yeah, if I heard you correctly, I think you said 120. Now notice what are the things that you are getting. For a hexagon, you got 60°, 120°, and 180°, right? For octagon, what do you think are possibilities?
90.
Okay.
130.
Come again?
130.
135. Okay.
Double two sub.
Now look, you have to be careful. This angle of rotation, does it have to divide 360? Hmm? Doesn't it have to divide 360°? So think about that. Um, Especially in terms of the order, okay? It is very important to figure out this order of rotational symmetry. You divide this angle of rotation by that, okay? So order of rotational symmetry is 360° by angle of rotation, or let's say minimum angle of rotation. Okay. So what happens is, in case of an octagon, you can design an octagon which will be have rotational symmetry of the angle will be 45-degree. You can have an octagon with this kind of, which if you turn by 90-degree, it will have rotational symmetry, but not if you turn by 45-degree. And similarly, you can also have an octagon which will, if you turn by 180-degree only, then it will have rotational symmetry. Now, there is a connection with number of sides to these things. Okay, so if we want to check that, it's the best way to do it is through a table. Okay. So let's look at number of sides. Let's look at order of rotation and angle of rotation. Okay. Now, when it is triangle, you get 120-degree and you get 3. We will come to quadrilateral, or we can do it. For quadrilateral, what are the possible angles of rotation?
Regular.
90, 180,
And 90 and
180.
correct. Yes.
270 also this is correct.
Sorry. Okay. So we have got, oops. And these correspond to the orders.
Four, 2.
Yeah. So the order is going to be 5. Hexagon, you have seen it to be, let's just copy paste from the previous slide. So the orders are, now do you see a certain pattern in this? What are the possible order of rotation?
Forming a pattern for odd number and even numbers.
So how are the numbers in the third column related to the number in the second column?
It is 360 divided by the number of rotation will give the angle of rotation.
That is fine. But do you see a connection between the column, the second and the third column?
Maybe they are the factors, for example.
Yes, non-trivial factors. Okay, and you don't have to believe me, but think about it. Okay, when you are rotating, what exactly is happening? So if you take a big polygon, if you have factors, then you can partition those vertices. Okay, so say for example, you have a polygon whose side, this is a polygon which looks like, let's say, n times, this is not x but a multiplication sign, k, right? Or let's say n times n. Okay, now you can partition the vertices into n groups of m, and you can kind of rotate it like that. Okay, so that the first vertex moves to say a1, a m plus 1, a 2m plus 1, like that. Okay, and then the vertex 2, a2 will rotate from a2, a m plus 2, a m plus a2m plus 2, like that. So you can actually show that these will have orders nm, n, and m. Okay, now of course if you do get into prime factors, etc., you can get into further details. Okay, now in light of this, what we are interested in is the smallest. Now if a quadrilateral has rotation of order 4, meaning it can be rotated through 90 degree, it can be rotated through 180 degree also. So 180 degree is the most general case. Okay, so that is why we can take 180 degree. And the important thing here is that a quadrilateral is 4-sided. 4 is an even number. Okay, and it's interesting to observe that if you look at hexagon, it is not necessary that every hexagon will have an order of rotation 3. The one that I had annotated before, okay, it will never have a rotation of 180 degrees. So you can see that there is no common such thing here. Okay, in this case, yes, you can take a the lowest, the highest common factor is 2, but in this case the highest common factor of all these is 1, because 2 and 3 are co-prime. So in case of a hexagon, you cannot say that there is one particular angle by which it will definitely rotate. Okay, so anyway, so as you can see, when you look into this question, you actually get a very interesting result out here. Okay, and you can continue to explore more more polygons to see what kind of pattern it will unearth, etc. So, and it nicely connects geometry with numbers. Okay, so it's kind of interesting that way. Now, this one, also I would like to say that once you assume this, once you get that, okay, that it has rotational degree of order 180 degree, the way you argued, those of you who did argue, that was very nice. Okay, all you need is okay, I'm going to annotate again because that will be faster. So here is one quadrilateral with rotational symmetry. Okay, and let's call it A, B, C, and D. Now, if you rotate it by 180 degree, then I'm going to change color and show where the things will be. So this will be the image of A. This is where A is going to come. And this is where C is going to come. Similarly, this is where D is going to come, and this is where B is going to come, right? So then you can show that AD is the same as BC, right? And you can show that AB is the same as DC, and therefore opposite sides are equal. Now, the moment you have a quadrilateral with two pairs of equal opposite sides, that is nothing but a parallelogram. Okay, and that's it. You don't need anything further. And I must admit that this is a simpler proof than what I had thought. So congratulations. Thank you. I will acknowledge you guys whenever, you know, this comes out as an article or whatever. Okay. Now, this next question. Okay. So you all made the correct assumption that the line symmetry needs to pass through one vertex, and we can call it A. Okay, so let me again annotate. So this is the line of symmetry, and A is on this. Okay. Now, B and D, which are on either side, have to be on either side, right? And you do need to point out that if B is on this, if AB is on this line, then what happens? Okay? Because then basically the whole quadrilateral collapses to a line segment basically. So that is not possible. Now, once you have got this, that you have distributed B and D, where should C be? Now, if C is not on the line, then C needs to have an image, which is also a vertex of the quadrilateral. And we have exhausted all the vertices, right? So the only possibility for C is to be again on the line. Okay, so that needs to be argued out. Okay, and rest of the thing, once you have placed this, then the rest is pretty straightforward, which you have also done. So you can basically, you know that B and D are mirror reflections of each other. So therefore AB equal to AD. and BC equal to CD, and that's by definition a kite. Okay, so that part is fine, except that you need to argue why C should be on the line of symmetry. Just like in the previous case, you need to point out why this thing, why it has to be 180 degree. It has to rotate by 180 degree. Okay. So that is good. Now for the next one, I will present it. So okay. Forget to remove the annotate. Okay. Okay, I need to remove these, otherwise it's not going to show. Okay. 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 How many lines of symmetries are there of a square?
8.
8. Are you sure?
Sorry, 4.
Okay, okay, that makes sense. Now, some of them came from the kite. And which ones are those?
Through vertices.
Through the vertices, right? So essentially, they have a name. What else can we call them?
Diagonals.
They're the diagonals, right? And then you have some which came from the isosceles trapeziums. So how can you describe them?
The adjacent angles are equal.
Come again?
The adjacent angles are equal and the diagonals are same in length.
See, one kind of line symmetry are the diagonals. They came from the kite. Okay, but there are two more. There are two diagonals. So two lines of symmetry are the two diagonals. There are two more, right? So how can you describe them?
Through the sides.
Through the sides. You can be more precise and say perpendicular bisectors of opposite sides, right? So those came from the isosceles trapezium. Okay. Now what happens? This is a very, very interesting thing. What happens when you have two lines of symmetry? Okay, so let's take a look. So, so this is from the kite. Okay, let's just start with one. Kite has one line of symmetry. We'll start with one. And this is from the isosceles trapezium, EF. Okay. Now, what we can do is we can flip AC on EF. EF is a line of symmetry. So, they intersect at O. Okay. So, first we are flipping EF on AC. Okay. And when you reflect a line of symmetry, the resulting line should be another line of symmetry, right? Okay, I'm just jumping ahead a bit, but you can see what happened. Okay, why they doubled. Kite had one line of symmetry passing through the vertex. Isosceles trapezium had one line of symmetry passing through its sides. Okay, in square there are two like that. So this is how the second one came, because the first one was reflected on the diagonal. Okay, and similarly, you know, the diagonal AC line of symmetry can get reflected on EF, and you know the other diagonal also becomes a line of symmetry, right? So that's what happens. That's where you see, like, you know, 1 plus 1 and you get not just 2, but in this case 4. Okay, so this is a quite interesting situation, and maybe we shouldn't call it 1 plus 1. Okay, they literally multiplied in some ways, multiplied in the commonsensical way, not in the product mathematical way. Okay, they grew. Okay, now Now let us take any point which is along a side. Let's take a point X on AD. Okay. Now, if we reflect it on EF, see here it goes. Okay, X dash. Now let us reflect it on AC, and this is where it goes. Okay. Now, if you want to look at the combined change from X to X double dash, one way to think of it is to connect it to the center O and look at it. You can still think of it as double reflection, which it is, right? Especially if you add the line OX dash. It is not shown, but I'll just annotate. Okay, if you draw this line, then again you can see that, you know, it's a double reflection. Okay. However, the other thing which you can see more clearly is if you consider this triangle DOX, and obviously you know that D, if you reflect on EF, D will go to A, and if you reflect on AC, it will remain wherever it is, right? So, in short, the triangle DOX has now shifted to AOX double dash. Okay. So, what has happened? Okay. So I'm at the end of the animated part. So let me just type here. What how let's say consider triangle TOX and triangle AOX double dash. Okay. What is the transformation? Okay. What would you say?
Rotation of 90 degrees.
Exactly. Now, the interesting thing is, again, if I annotate, you will see something quite interesting. Now, notice this angle is the same as this angle, and this angle is the same as this angle, right? So the gap between these two, this was 45 degree, and that you can see how that doubled here to give you a right angle. Sorry. Okay. So when you reflect twice on intersecting lines, you get a rotation, and the angle of rotation is linked to the angle between the two intersecting lines. Okay, and you can explore what happens if you reflect on two parallel lines. Okay, so, and these can be done very nicely with a bit of paper folding, etc. So, as homework, I will again ask you to read this because I believe it does include those things. Okay. Also, try the following with paper folding. Okay. So the first one is reflect twice on intersecting lines. Reflect twice on parallel lines. Okay. If I remember correctly, the article above do have some pictures which can guide you, and it's a fun thing to do. Okay, parallel line is easier to do. Intersecting lines is a slightly harder because the paper gets folded weirdly, but I think you should be able to manage. The key idea is you take a piece of paper and you draw two lines like this. Okay, make sure there is sufficient space around, and you can draw ideally, okay, a scalene triangle here. Scalene because then when it rotates or reflects, you will be able to identify the three sides very carefully. So what you do is you fold along this. Okay, you fold along this line and you find its mirror. You basically, you use the pen to mark these vertices. Okay, to mark the vertices using a pen. Basically, you fold it, this is there, you put the pen here, you put the pen here, and kind of poke it with the pen so that you will get these vertices on this side. Then you open and see these vertices, you join, you form the triangle. Okay, then you can again do the same on along the second line, this line. Okay, and you should get three more vertices, and then you can kind of see, okay, what happened. Okay, and similarly you can do it with parallel lines. Okay, in case of parallel lines, it's easier because you do it you fold it once and you are kind of done. Okay, and see what all you observe. There is a worksheet also on dot sheets which you can try. So let me just share the link also. 1 second. Okay, I'll try to see if I can find it faster. Sorry. Okay, I have no idea why it is copying it somewhere way over there. Okay, no idea. Maybe okay, let me try now. No, okay. So somehow it is throughout for some reason always copying there and not here.
You
That's
can
very,
put it
very
in a chat box.
okay. Yeah, I'll do that. Okay. There. Okay, sorry. So yeah, you can try that. The last bit has this, reflecting twice on dot sheet. So you can try that too. Yeah, so that's all for today. This is not too much of a homework, but explore this symmetry aspects and yeah. So maybe I will send you more homework by end of today. Okay. So that's all. See you next week. Bye.
Thank
I'll
you,
stop
Shweta.
sharing.
Bye.
Thank you. Bye.
Thank you.